Welcome to Pre-Calculus, Unit 1, Function Analysis. In this video, we're going to continue our discussion about how to analyze and understand the functions, the properties of functions. In this video, we're going to talk about increasing, decreasing, max, and mins of functions. All right, so here is a little bit more detail of exactly what we're going to do. We're going to find intervals for which a function is increasing, decreasing, or constant. We're also going to talk about what that means. Then we're going to find relative, or some people call them local, or absolute mins and maxes of graphs. So we'll talk about what all those keywords mean here in a moment. All right, so first off, let's talk about increasing. A function is increasing on an interval if for any 2 points a positive change in x results in a positive change of y. So if we're thinking about a graph here, and we have a function that maybe is doing something like this, and we would say, okay, on the interval from here to here, right, from A to B, any increase of x starting from A and going to B results in a positive change for f of x. So basically that means if you follow along on the interval A to B, starting here at A, if you follow along on the graph, every time you move to the right, every time your x value gets bigger, the y value also gets bigger, hence increasing. Decreasing is when a function is decreasing on an interval if for any 2 points a positive change in x results in a negative change in f of x. So we're always looking at, I don't know what that was, sorry about that. We're always looking at a positive change in x. Okay, so here's my function maybe, and we would say, okay, looking from here A to here B, as we move from a x value of A and it slowly gets bigger and bigger and bigger and bigger, the corresponding y values, that's the actual graph, are getting smaller and smaller and smaller. They're decreasing. Hence, as I move across the graph from A to B, from x value of A to x value of B, every time x goes up, the y value correspondingly goes down. That's obviously negative or decreasing. A function is constant on an open interval if for any 2 points a positive change in x results in 0 change of f of x. So if we have a graph that maybe does something like this, right? What we notice is that from here, A, to here, B, as x went and got bigger, x was increasing from A to B, we notice that the actual function itself did not change at all. It stayed the same. So maybe here it was 2, and then it was 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, and it was always 2. There was 0 change as we moved from A to B. That is where a function is constant. So here's a nice looking graph where we actually see these three things all at once. So what we would do in this is we would talk about the fact that on the left-hand side here, from -2 to 0, the graph is decreasing. As I move left to right, the graph is going down. And from 0 to 2, as I move left to right, the graph is staying constant. It's not increasing nor decreasing. And from 2 towards 4, the graph is increasing. So make sure that we understand that when we talk about where's the graph increasing, where's the graph decreasing, we do so in interval notation. So if I said, describe for me where the graph is increasing, you would say, well, it starts increasing at 2 and it increases till 4. So that's an interval from 2 to 4, and in that interval, the graph is increasing. And I could say, all right, well, where's the graph decreasing? And you would say, all right, well, the graph is decreasing from -2 to 0, from -2 to 0, those x values, along those x values, the graph is decreasing. And finally, where is the graph constant? We would say the graph is constant from 0 to 2. From 0 to 2, those x values in that interval, the graph is not going up nor down. Now, notice I didn't use brackets because a bracket means that you're talking about being at that particular value. And for example, when I'm at 2, it's just a single point. A single point is not increasing, decreasing, or doing anything. It's just a single point. So that's why we always use parentheses when we're talking about increasing and decreasing and constant. So when we describe what a function is increasing, decreasing, or constant, we do so by defining an interval of x values. The y values don't matter, right? We know based on looking at the graph that the y values are going up or down or staying the same. But where we want to give the answer as an interval of x values for which that is happening. So please remember to use interval notation. Remember, always use parentheses as I just mentioned. And it obviously helps tremendously to see a graph. If you could see a graph, it makes it so much easier to talk about when the graph is increasing and decreasing. Let's do a couple more examples. If you actually want to try these out on your own, hit pause or fast forward, whatever you want to do, and then do them and then pop back up and see the answers. That's fine. But let's talk about this first graph, and one thing you could do is just kind of put your finger on the left side of the graph and start tracing it, and you'll notice that my finger is always going up. It does slow down right here in the middle, but it is still always increasing. It does, I agree, it does kind of look like it flattens out, but technically it really doesn't. It's just very slow there in the middle, but it is always increasing. So this graph is increasing from negative infinity to infinity. It's always increasing, so you don't even have to talk about decreasing or constant. All right, how about this graph right here? It does increase, and then it makes a change at -1, and then it decreases and makes a change again at +1, and then it increases. So there are two places where this graph increases. It increases from negative infinity to -1. So that's right here. It's increasing. And then it's also increasing from +1 all the way towards infinity. Now, it's important to note that that infinity is not infinity up, that's infinity to the right. Remember, we're talking about from the interval 1 towards infinity. In that interval, here at 1, all the way towards infinity, the graph is increasing. From the infinity, negative infinity to -1, in this interval over here, for all those x values, the graph is also increasing. Now, remember, when we put two intervals together, we put a little u in between them for the union. Now, where's this graph decreasing? Well, it's decreasing in the middle from -1 to +1. In that interval, it is decreasing. So -1 to 1, the interval that we skipped for increasing is the interval where we are decreasing. All right, this next graph does all three. So let's talk about this graph. From negative infinity to 0, we are increasing. So negative infinity to 0, remember those are x values. So here's negative infinity all the way until we stop at 0 right here. In that interval, the graph is increasing. Where is the graph decreasing? Well, it starts decreasing here at 2, and then it decreases for all x values greater than 2. So that'd be 2 towards infinity. And finally, the graph is held constant between those two values, between 0 and 2. So between 0 and 2, the graph is being held constant for those x values. So very, very easy to talk about increasing, decreasing, and constant. It's a very, very simple idea, very simple. All right, so let's practice it out. Now, if you were given this function right here, you might say, boy, I don't know when this function increases, decreases. So that's where really making a graph is so helpful. So one thing you could do is use your calculator or Desmos. I love Desmos. It makes beautiful graphs. So all you got to do is type in f of x equals x plus 2 quantity squared, and you should get a graph that looks something like this. Now we could easily see, and now we can easily trace, the graph is decreasing, 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 decreasing. Right here at -2, it looks to turn around and start to increase. So where is the graph increasing? Well, it increases starting at -2 towards infinity. Remember, that's not an infinity up, that's actually an infinity this way. So all x values, -2 towards infinity. In that interval, the graph is on its way up. And the graph is decreasing from negative infinity to -2. So once again, negative infinity is way over here somewhere. So all this way up to -2. In that interval, negative infinity, -2, anywhere in that interval, the graph is decreasing. All right, let's look at another example here. Once again, it's really easy to do this with a graph. So first thing you do is type this into Desmos or on your calculator, take a look at a graph. And this is actually a really funky looking graph. A lot of weird stuff is going on here. Let's quickly go back to the function. Let's make sure we understand what's going on. We could factor that denominator, and we realize that there are two values, x equals -1 and x equals +1, that I cannot be because they make the denominator 0. And that is what produces these these vertical asymptotes at -1 right here and +1. All right, so this is a crazy looking graph because we see a lot going on. So on this left portion of the graph, we see an increase. It's increasing all the time, right? So therefore, we are increasing from negative infinity up into negative 1. So from negative infinity to negative 1, it's always increasing. Now, we also see this part in the middle here, which is kind of an interesting. It's like a little parabola, you could say, in the middle here. And it looks like if I follow that graph, starting at negative 1, I'm also increasing until I hit 0. And I hit 0, I make a switch to decreasing. So we would say union negative 1 towards 0, I am increasing. So I'm increasing all right here, and I'm also increasing all right here. Now remember, I had to skip over negative 1 because negative 1, there's a vertical asymptote. Nothing's happening at negative 1. I'm not increasing, decreasing. I don't even exist. So that's why I had to make sure negative 1 got skipped. All right, where is this guy decreasing now? Well, I start decreasing at 0, and then I'm decreasing, decreasing, decreasing all the way until 1. So 0 to 1. And then again, 1 is an asymptote, so I do have to skip over it. But after 1, I'm still decreasing on the other side of the graph here. So I'm going to do a union 1 towards infinity. So that's kind of a weird looking graph, but it's nice to talk about where it's increasing and decreasing. All right, now one thing you may notice is that when graphs make a switch from increasing to decreasing, it oftentimes, not always, but oftentimes happens at max or mins, maximums or minimums, which you should be familiar with the graph. So we call these max or mins extremas, right? Extremas. These are values that are extreme, right? Extremely high, extremely low, max, mins. If we think about this graph right here, if I were to just draw a quick rough graph, right? I say, oh, here's a graph. Oh, look how cool this graph is. This graph is so much fun. Okay. Now what you'll notice is that there's several different turns. So I'm increasing, and then right around here I stop. And I start to decrease, 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 and I stop again. And then I increase, 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 and I stop again, and then I turn and I decrease. So every time we make that kind of transition, we create these max or mins, these humps or these valleys, right? Well, as we're going to learn here in a moment, these are all called extremas, right? You don't have to use that word if you don't like it. I really don't like it. It's kind of a weird word, but max and mins, right? But we define them differently. A true max, an absolute global max. A true max is one point that is higher than every other point on the graph. There's no y value bigger than 7. There's clearly a max here at 7. There's no y value above 7. That's a true max. But this right here is also called a max. It's just not called a true max, right? Because this isn't the highest point of the graph. There's clearly all these other points over here that are higher than this point. So this is what we call a relative max, meaning relative to this particular interval. Like if I say, hey, from here to here, relative to that interval, this is the highest point in that interval. So relative to this specific area right here, it is a max, but it's not the absolute max because that is over here, if that makes sense. Now, because these arrows are both going down forever, there is no absolute true min because this is going down, down, down. So there's not one point that is truly lower than every other point because those lines are going down forever. So there's no true min or absolute min in this graph, but this right here would be a relative min. Because relative to this general area right here, this point right here is lower than all the others. So we have this idea of max and mins, humps and valleys, but we have to understand that some of them are relative, meaning in their general area, their mins or maxes, and some of them are absolute, meaning truly the biggest graphs. So here's a little bit of a textbook definition about maximums, right? So a local maximum of a function is a value f of c that is greater than or equal to all range values of f on some open interval. So let's talk about this sentence real quick here. So first off, it says a local max. I was calling that a relative max earlier. There are two terms that different mathematicians use that mean the same thing. Local or relative. Local meaning local to that specific area, right? In that locality, it is a max. Now remember, f of c is just a fancy way of saying y. So what we're saying, a relative or a local max of a function is a y value that is greater than all or equal to all other values of f in some open interval containing c. So I'm going to go back to my very messy graph here. But what we're saying is like this right here is a local or a relative max, right? If I were to look at a local area, an interval from say -10 to -5, in that interval, this y value of this point is higher than all other y values. That's a local or relative max. Now, if the y value, which again, remember, f of c is just a y value, if the y value is greater than all other range values, then it's considered a true max or an absolute global maximum. And I can give the exact same definition for a min. A local min of a function f is a value, f of c, right? Or, again, remember, y. It's a y that is less than or equal to all other values of f in that particular interval. A local min is also known as a relative min, meaning local or relative to that particular area. It is the lowest value of all. But if the y value, which again, f of c is a fancy way of saying the y value, if the y value is truly less than all others, it is considered the min, okay? Now, one question I often get is, can a graph have two absolute max? And the answer is yes. So if a graph goes up like that, comes back up again, and these 2 points right here are both tied, like maybe this is -2, 7, and maybe this is +5, 7. Well, they both have the highest y value, 7, of all other points. So those are both absolute or global maximums, okay? But remember, since these arrows are going down, this right here would be considered a relative min, because local to this area, it is a min, but it's not the overall min. Let's look at a couple more kind of random graphs here to kind of make sure we see these ideas. So here's a graph, and if you can't see the ends, it's implied that this is going up forever. And if you can't see this end, it means it's going down forever. So these right here are considered relative mins. Sorry, that went away. Relative mins, because remember, this arrow right here indicates that the graph is going down forever. So that means that relative to this area and this area, those are minimum values. But it's not absolute mins because the graph is going down. Same thing right here. This is a relative max. This is a relative max because this arrow indicates that the graph is going up forever. So hence there is no true absolute max. Here's another example where we see a absolute max, a true max right here. It is higher than all other values. These are going down forever and ever. And then this is a local or relative max because local to that specific area, it is a max. And this is also a local min right here. Here's one more graph where we see, again, this is implying that this is going up forever, down forever. So we see a local min, another local min, and two local maxes. But because this side's going up and this side's going down forever, there's no absolute or global maximums or minimums. All right, so one final thing we like to do is, this is going to be something I could do on a test or quiz, right? Is, hey, here's a function. Tell me when it's increasing, tell me when it's decreasing, and give me the relative max mins or absolute max mins if there are any. So the one thing that I've kind of stressed in this video that makes all of this very easy is taking a look at the graph. This is where Desmos comes in handy. So if you go to Desmos right now and type in x to the fourth minus 7x squared plus 6x, you'll get a nice graph like this. And if we're looking at this graph, we definitely see right here, for example. And the cool thing about Desmos, all you got to do is click on it and you could see the point. This is a relative max. These left and right ends are going up forever and ever, so I could clearly see that it's going up forever. But this value right here does appear to be a relative max. That's pretty cool. And that's the cool thing about Desmos. All I got to do is click on it. This right here would be a relative min, 1.6, comma negative 1.766. And then again, the cool thing about Desmos is you could zoom out or you could drag it around. And we do see all the way down here, there is a true absolute min. There is no point lower than that point right there. And then if we look towards the upper values, we see that these lines are going up forever and ever and ever. So there is no absolute maximum. All right, we could zoom way out to kind of see all of this at the same time. It's obviously very small, but we can still see it. And the cool thing is now we can understand decreasing and increasing. So I'm decreasing from negative infinity all the way to negative 2.057. In that range, I am decreasing. I'm also decreasing from this relative max to this relative min. So from 0.456 to 1.601. In that interval, I am decreasing. And then I'm increasing where I'm not decreasing, if that makes sense. So from negative 2.057, that x value, all the way to 0.456, that x value, I am increasing. Then I'm also increasing again from 1.6 towards infinity. Okay, so remember, when you give those increasing, decreasing intervals, you got to be very clear that you are giving x intervals of x values for where the graph is increasing and decreasing. Okay, sometimes that confuses kids. All right, so hopefully it's a nice view of the graph. It does look compacted. One thing you could do is if you click on the little wrench, you could change your x-axis. Maybe we want the x-axis to only go from I don't know, negative 10 to positive 10, and then you can kind of see a little bit of a nicer graph there. It looks a little prettier. It's not so condensed. And you could still click on the points, and you could see these absolute mins, relative max. You can even click and find the zeros if necessary. Sometimes those zeros are needed as well, but you don't change from increasing to decreasing it necessarily in zeros. But anyway, you get the point. Hopefully this all makes sense. But the number one thing when you're talking about increasing, decreasing, and relative max and mins is really making a graph. It really kind of makes it nice and pretty to take a look at. All right, guys, that's it. Hopefully you understood everything. It was all pretty easy, and I will see you guys in the next video.